Excuse me. So we have completed most of SHM, but some problem solving methods and techniques, etc. we'll continue to discuss. So let me just refer to our last lecture once. Meanwhile, if you have any doubts and questions from HC Verma or the module in simple harmonic motion, you can send me the question number. I'll start with the discussion of that also. Yeah, so we had just about finished up with the discussion about physical pendulum in the last lecture, and we will see some examples of application of that. But before that, we've discussed quite a bit about spring mass systems and simple harmonic motion with combination of springs, etc. So especially if you have some questions and doubts, please let me know. We'll discuss the same. So I'll start today's discussion with a question based on spring mass systems. Just give me a moment. Okay, so let's look at slightly more advanced type of an example problem. So both of these are massless smooth pulleys. So in this example, the spring constant is given to us as 12 newtons per centimeter. The mass of the block is 3 kg. G is equal to 10 meters per second square. The block is released from a position with a spring at natural length, and the thread taut. Basically, the thread is just about tight. So we have to find omega and time period for the blocks SHM. Then we have to write the amplitude and we have to also find the maximum speed of the block during its SHM, and we have to find the maximum extension of the spring. So let's try out this question. So what I would suggest you do here is first of all, analyze the equilibrium position of the block, the mean position. Then analyze its free body diagram at some displacement from the mean position. And this will give us the dynamics of Shm. And then finally analyze the initial state. So use the initial state to find the amplitude and phase constant. So pretty much similar steps that we use in all Shm problems, same we have to do here also. Just try this out, people. We'll discuss. Okay, people. So I'm analyzing the equilibrium position first. Okay, so step by step, I'll take you through all the things we need to do here. So let's say this is our equilibrium condition. So the acceleration of the block should be 0. In this state. So acceleration is 0. That is our mean position. So whatever tension the string is having should balance the weight of the block. Let's say in the equilibrium condition, the spring has an extension of x0. So we have this and we have K x0 is equal to 2t0. So from this we have right. Okay. Now from this equilibrium position, if we have given some displacement to the block, okay, so compared to this above position, so between this to this has got a further displacement of delta x. So now this has become L plus x, where x is equal to x0 plus delta x. So we'll also understand that with respect to the equilibrium position, this would have got a downward displacement s of how much? Tell me how much s should be in terms of delta x. Now the important thing is we have to find this relation s in terms of delta x, constraint relation. Please work out the constraint relation and tell me. That is the key to solving this problem actually. Anybody can please work out that constraint relation and either tell me or send it on the text message. Yes, very good. Tantresh, that's correct. So you see from thread length here, okay, that if the pulley moves from a position like this to a position like this, it moves by delta x. So this much thread gets released. So the block on the other side will have to move from this position to 2 times delta x. So this s is equal to 2 times delta x. So when we write this equation here, finally, this becomes 2 times, oh sorry, this is the other way around. Kx is equal to 2t, my mistake. So Kx is equal to 2t. So before that, you can see this relation is there. These are equation 1. And now here, these together tell me that Kx by 2 minus mg is equal to ma. So further resolving that, we have k by 2 into x naught plus delta x minus mg is equal to ma. And now from this, we can see that we can substitute delta x as s by 2. So we have k by 2 x naught plus s by 2 minus mg is equal to minus m d2s by dt square. So this is our second equation. Now from equation 1, when I substitute this will become this equation will now become d2s by dt square is minus k by 4m s. This is the SHM equation. This is SHM with omega square is equal to k by 4m. Depends. You want to write downwards, it's mg. But see, you have to understand one thing. No? You have gone beyond the equilibrium point. So the acceleration will be at upwards now. So see, T naught was equal to mg. Okay. Now T is greater than T naught because x is greater than x naught. So that means this tension is greater than mg. So that's why the acceleration is upwards. Okay, so you got omega square. Now you can work it out numerically from k and m and all that given. And now the rest of the things that are left is the standard SHM concepts, that from the dynamics of SHM, you'll write the SHM equation that x is equal to a sine omega t plus phi, where amplitude a and phi you will have to find out by using the initial conditions.
Excuse me, sir.
Yes. Yes, you had a question, Beta?
Yes, sir. Can you please scroll it up? Actually, I did not copy the entire question.
Okay. So the values are on given. Basically, see, these are the values you'll require to solve it. So I'll put the values here. Okay, now what we have to also remember is this constraint relation, that x is equal to x naught plus delta x. Which now means that x is equal to x naught plus s by 2. Okay. Now let's work out all these values numerically. X naught, which is 2 mg by k, here will become 60 by 12, so 5 centimeters. And omega square will become 12 into 10 raised to 2 divided by 12. So omega will be 10 radians per second. So these are two additional things. So x is equal to 5 centimeters plus s by 2. Now you can see that at t equal to 0, x was 0. So that means s is equal to how much? Minus 10 centimeters. Okay. And initial velocity was 0. So this is telling me that a sine phi is minus 10. This is telling me that a omega cos phi is 0. So this set of things is now telling me that phi is minus pi by 2 and a is equal to 10 centimeters. So the block's SHM is that its downward displacement from the mean position is 10 centimeters sine 10t minus pi by 2. And is also telling me that x as a function of time is x naught plus s by 2. So x is equal to 5 plus 5 sine 10t minus 5 or x as a function of time also be written like this. Five into 1 minus cos omega t. So from this, we're also getting the idea that the maximum extension of the spring is 10 centimeters. When cos 10t will be minus 1, or 10t will be pi, 3 pi, etc. So the time x. So x ranges between 0 to 10 centimeters. It's 0 at t equal to 0, t, 2t, this, and it's this at. So that is as far as the extension of the spring is concerned. Okay, people, so hope this is finally clear to all of you. So as far as the block is concerned, with respect to its mean position, it will be oscillating between 10 centimeters above it and 10 centimeters below it. So the block will be doing this. If this is the mean position, it will be starting from here at t equal to 0, with initial velocity 0 at 10 centimeters above this. And it will be starting with the maximum acceleration. And by the time it comes to the mean position for the first time, it has maximum speed like this. Okay. And we continue going forward. And again, come to rest at t by 2 time. But this time having the maximum acceleration in the upward direction, 10 centimeters. Then again, it will pass through the mean position having v max. And again, it will be back to the mean, this position at t equal to capital T. And again, all the way back down like this. So we keep doing this oscillation. So this oscillation where we're writing the displacement from the mean position at some time t as a function of time, that is actually our 10 centimeters sine omega t minus pi by 2. This is your S equal to minus 10. This is your S equal to plus 10. This is your S equal to 0. This is your SHM of the block. Okay. And during that time, if you look at the extension of the spring, that will be doing this. Yes, Vashisht, I will do that. Okay. So now you can also see that for this given equation, of course, our omega was 10 radians per second. So time period is pi by 5 seconds. Okay. But also you can see that V max is equal to A omega. So 10 centimeters into 10 radians per second. So maximum speed of the block when it's passing through the mean position is in fact 1 meter per second. And maximum acceleration, A omega square, you expect it should be G actually. Basically equal to G. Now you can understand why it's equal to G, because at this position, this acceleration will be G downwards. Because the tension is 0. Whereas at this position, the acceleration will be T minus mg divided by m. Now the tension at this position will become 2 mg. So it will be G upwards. Okay, so these are some finer details to understand about the SHM. So Vashisht, I'll scroll up just a moment, let everybody just understand this part also. So another thing that you can understand here, that when the spring is at a position of 5 centimeters, that is your mean position actually. That is when the block is at S equal to 0. Because that is the relationship, that X is equal to 5 minus S cos omega. So S by 2. Whereas okay, so this is a slightly more advanced type of problem for your JEE Advanced level. So I'm just scrolling back up. Vashish, just let me know which part you want to note down again. Is it this part, Vashish? Okay.
Done, sir.
Okay. So I hope this aspect of simple harmonic motion is clear. Now we'll come back to an example with angular harmonic motion. So we were discussing last time in general angular harmonic motion. That is the angular oscillation such that the angular displacement is a harmonic function or a sinusoidal function of time. Okay, Tej. Okay, so just waiting for you to write down this maximum velocity part. The maximum acceleration was not asked in the original question, but I've included it in the solution here. So to just calculate a omega square. Okay, so let's come back to the discussion about angular harmonic motion. So in this, theta is the angular displacement from the mean position. So the mean position is theta equal to 0. And at the mean position, we will see that the net torque becomes 0. So because from this equation, we now have that angular acceleration is this. If we double differentiate this, we get this relation, which means that the net torque is equal to something like this, where K is equal to moment of inertia into omega square. So we have a restorative torque, which is proportionate to angular displacement. This becomes the dynamical condition. So further, based on this, we have done the derivation of time period formula for a physical pendulum, which we'd seen depends on two things: the moment of inertia about the axis of rotation and the distance of the axis of rotation from this center of mass. And of course, it's also subject to the condition that the angular displacement should be small. So in that sense, we say that when a physical pendulum is doing small oscillations, that is, its angular amplitude is a small angle, then it's actually doing a harmonic oscillation. So small oscillations of a physical pendulum constitute angular harmonic motion, for which there is then a formula for the time period. So what we've seen about the physical pendulum is that, let's say, this is some kind of a rigid body with a hinge at the point P. Now, at a position where the center of mass is vertically below, what will happen is torque will be zero. Okay, so this will be the mean position. But the moment we take it to some angular displacement with respect to this, then we are in a situation where the weight of the object acting through the center of mass is creating some torque about the point P. So if this angle is theta, then you can see this moment arm will become d sine theta, and this will produce a torque like this. So this torque will become mg into d sine theta, and where I is moment of inertia about the point P, and alpha will be written as minus d2 theta by dt square. So we get the equation that d2 theta by dt square is minus mg d sine theta divided by the moment of inertia. Now the important thing is that this can be approximated as minus omega square theta for theta being a small angle. So sine theta can be approximated as theta, and omega square becomes mgd divided by I. So the time period becomes so now we'll also see today that simple pendulum is a special case of this. So we'll understand a simple pendulum as a special case of this situation. In a simple pendulum, we have a massless thread of length L with a particle of mass M attached. So if we take this massless thread through an angular displacement theta, then we can see that the weight will give an angular acceleration alpha. So mgl sine theta will become ml square into alpha. Because the moment of inertia about this point P would be ml square. So we have the formula that alpha, which is minus d2 theta by dt square, is g by L sine theta. So for small theta, this is our angular harmonic motion. From this we can see that we get this standard formula that we are familiar with. But now you see the derivation of this. Okay. So just make a note of the case of the simple pendulum as an application of the general formula for the physical pendulum, but very easy example of that because the moment of inertia is just ml square. We have a single particle at a distance L from the axis of rotation. The thread is massless, so moment of inertia is just ml square. And the center of mass of the whole system is at the position of the particle only. So its distance from the axis of rotation at P is again L. So in the left hand side formula where we have that mgd divided by I term for omega square, we'll replace d with the length of the string L, and we'll replace moment of inertia I with ml square. Yeah, Aditi, I'm explaining the simple pendulum part again. You can see simple pendulum consists of just a single particle, which is basically called the bob, like a tiny sphere attached with a thread of length L. So the vertical position of the thread is the equilibrium position or the mean position because the torque is zero. But the moment I take it to an angular displacement theta, it try to swing back because of the torque produced by mg. You can see that in the second diagram, mg is acting along this line. So what is the moment arm from the axis of rotation? That is this one. So that is L sine theta, this distance is L sine theta. So mg multiplied by L sine theta, that is the torque. That should be equal to I alpha. So I is ml square into alpha. And theta and alpha are in opposite directions. So alpha is minus d2 theta by dt square. Is it clear now, Vital? Okay. Okay. Now let's look at
Just a
another.
minute. Can you please put it up?
Okay. Okay. Yes, exactly. Aditi. That's correct.
Done.
You can see that if angular displacement theta is clockwise, then alpha will be anti-clockwise and vice versa. If I take it to the other side, so theta is anti-clockwise, then alpha will become clockwise like that. There's always a restorative torque which is acting. So next, let's look at another example, but this time using a actual rigid body kind of situation for the physical pendulum instead of a simple pendulum that just consists of a single particle. So suppose we have this shape that our pendulum is like a T-shaped body, which we made using some material which has uniform thickness and uniform density. So basically uniform mass per unit length, and it is hinged at a point like this, so it can rotate freely. So this is a T-shaped inverted T, of course, a rigid body, such that this length here is L, or in fact, let's make it 2L, and the bottom part has a total length L, but it's attached at the midpoint over here, so this L by 2, L by 2. So T-shaped body made of material of uniform density and thickness. So of a thin rod-like material. So we have to find, now it is hinged at P such that it can rotate freely about a horizontal axis through P. So the axis is perpendicular to the plane of the diagram. So it's rotating like this. So we have to find the time period for small oscillations. What we mean by small oscillations is small angular displacement oscillations. Yeah. So we won't get into the derivation again. What we'll do here is we'll directly use the formula that for small angular displacements or amplitudes. Omega square is where m is total mass, okay, d is distance of center of mass from the axis at the point P, and I is moment of inertia about P. So we'll just use this directly. Okay, so time period is just 2 pi by omega, then given by the relation. So basically, what we have to do here is we have to use our knowledge of center of mass to find out D, and we have to use our knowledge of rotational mechanics to find out the moment of inertia, and then substitute in the formula. Okay, so let's see first of all how we calculate the position of the center of mass. If you're working on it, just continue. I'll just briefly tell you. Yeah, sure. So you can treat this section of the rod because it is of length 2L. We can treat it as if it's a mass 2L, because we can take M by L as mass per unit length. If you're working on this, just continue. I'm just explaining in case there are people who have not started or understood how to start the problem yet. So this section center of mass will be at the midpoint, it will be at L like this. And like that, now think of another rigid body that is the lower part. So first think of it separately before you join the two. So this is of length L. So accordingly, this one's mass should be M, and this one's center of mass should be here. Okay. So when we join these two together and we get that rigid body, now just use the superposition method. M1 x1 plus M2 x2, that kind of thing you can use. I want to say that with respect to the point P, there is one center of mass located here, another center of mass located here for the individual parts. This is L, this is 2L, but this has a mass of M and this has a mass of 2L. So the system center of mass should be somewhere. That is M1 plus M2. So first find this, and then your distance PC will become your D in the formula of moment of inertia. Okay. So that's one thing you do. And the second thing is that in the formula of moment of inertia, replace M. So that will be 3 times the mass of this thing. And third thing is find the moment of inertia for the system about the point P, about the axis at the point P. So you need these 3 things, because your time period will become 2 pi under root I divided by M. But remember, M is the total mass. So here it's not small m, it's going to be 3 times M. Just a minute, people. Just continue with the work. My system seems to be hung again. I think the audio and all is working. Just the white screen is not working. I'll just restart the white screen. Just continue working on the problem till then. Right. So here we go. So first thing, let's find D. So for that, come back to this diagram. From the point P, C1 with a mass of 2m is at a distance L, and C2 with a mass of m at a distance of 2m. So the system center of mass here at a distance d. So this d will just become basically m1 x1, let's say, plus m2 x2 divided by m1 plus m2. That kind of formula we can use. So 2m located at L plus m located at 2L. 4L by 3. That's done. Then we will replace m total as 3m. So that's also done. And the only thing is the moment of inertia. Let's come down to the moment of inertia. So about this axis at P, moment of inertia will be moment of inertia of the first body plus moment of inertia of the second. So the first thing is just like this. It's 2m. So this I1 will become ml square by 3, but so 8 by 3 ml square. The total mass is 2m. Length is 2m. The second one, for this one, the axis is over here. Distance of 2m. Whereas its center of mass is here. So I2 will be ICM plus md square, that formula. ml square by 12 plus m into 2l square. So I for the system will become so 32 plus 49 is 81 by 12. This is our I. So now, having got all the parts, we can calculate the time period. just check my final answer for the calculation part, but I think this should be correct. Okay, so hope this example is clear to all of you students. Fortunately, I got disconnected again. Anyhow, so we are now more or less done with simple harmonic motion. We have a couple of things to complete up in simple harmonic motion, which we'll discuss in the next lecture. One is damped oscillation. which is actually part of your JEE Mains syllabus only, not part of the JEE Advanced syllabus. And the other is combination of SHMs. So this and some more examples we'll do in the next class. Also, we'll do doubts from HCV and the module. Some of you have sent me some couple of doubts in the WhatsApp also. I'll pick up those doubts in the next lecture. Okay. Diti, especially you, I think you have sent some doubts from earlier chapters also. I'll try to pick up some of those doubts in the next lecture. That's
Sure.
it for today. Yes.
Sir, combination of SHMs is also a part of JEE Mains only, right?
No. This one is only damped oscillation. Okay, this is both these two things. Combination of SHMs is part of both advanced and mains. Only damped oscillation is exclusively for JEE Mains. Okay.
Okay, sir. Can you please scroll it up?
Yes, sure. So this example is clear, I hope. We calculated moment of inertia and D and then substituted in the formula. Okay, so that's it for today, people. Wish you all the best. Have a nice day.
Excuse me, sir.
Yes, beta.
Sir, can you please scroll it a bit more?
Further up. Okay.
Yes, sir.
This part.
Yeah.
This center of mass part.
Yeah.
Okay.
Sir, again, can you please go further up? Yeah, sure. And I also wanted, I actually missed out the question. So can you please take it up? The first question, the very first question, I missed it out. Only the question. Okay.
This one, beta.
Yes, sir. Done, sir. Thank you, sir.
Okay.
Bye, sir. Thank you.